pressing this, or is this on?
No.
Good. Okay. All right. Well, I'll get started today, and basically what I'm going to do is catch everyone up on what we've been working on most recently, which to my mind effectively is anchoring this stickers and spacers model for phase separation. I say multivalent proteins here, but I will also bring up RNA in the back third of this talk. So just as a way of providing context and getting through the background quickly, it's now well appreciated that multivalent proteins and RNA molecules are what Tony Hyman and Mike Rosen have taken to referring to as scaffolds that drive intracellular phase transitions. Now, the way we will sort of think about multivalent molecules is that from a synthetic polymer standpoint, these really are best thought of as associative polymers, which in the language of Semenov and Rubinstein is basically described as polymers or macromolecules that have attractive groups interspersed along the linear chain, which will fit this typical sort of stickers and spacers architecture. So I'll walk you through what I mean by that. So here's, let's say, a linear polymer. The sort of bluish colored ovals are intended to represent the stickers. These are the groups that are capable of making attractive interactions. They could be motifs in intrinsically disordered regions that happen to have, let's say, aromatic groups or charge residues or specific types of polar amino acids. But the key distinction between a sticker and a spacer is as follows. In terms of attractive interactions, the stickers will always be stronger in terms of sticker-sticker interactions. So anything that sort of is inferior in terms of attractive interactions to the sticker will end up being classified as a spacer, so much so that the spacer can actually sort of encode predominantly repulsive interactions because it really likes the solvent, or it could have sort of weak attractions when compared to the actual stickers themselves. And this is a much more relevant framework for thinking about the driving forces for phase separation. And it turns out it's not just for intrinsically disordered proteins, but it actually can be adapted to, folded molecules connected by disordered linkers, and as I will demonstrate, even for RNA molecules as well. So the obvious question that arises is, if we are to, let's say, leverage the power of this particular theoretical formalism, then one of the things that we'd like to be able to do is to look at a sequence and figure out what sort of stickers and spacers are encoded within the sequence, or what sort of stickers and spacers might become emergent as a consequence of post-translational modifications or oligomerization or things of that nature. Now, in systems such as this, popularized by Mike Rosen, identifying the stickers and the spacers actually becomes fairly straightforward, because what typically one has are interaction sites on a folded domain. So in this case, in this Pac-Man representation of the SH3 domains, essentially the mouth of the Pac-Man is intended to denote the binding site for the proline-rich module. So effectively, together, these make up complementary stickers. And as Mike showed in this beautiful paper now, roughly 8 years ago, is that the valence of the SH3 domains, i.e. the number, and also the PRMs, will basically determine the driving forces for phase separation. And subsequent to that work, work that Tyler Harmon did in my lab, demonstrated that specific properties of the linkers, which will serve as spacers, will actually determine whether what you get are sort of spherical condensates fully networked, or whether you just make sort of test tube spanning gels, right? But so in this case, there is no fundamental challenge to sort of identifying stickers and spacers. The particular challenge that might be in play is working out the properties of the spacers and or whether there are auxiliary stickers resident inside of the disordered linkers. But of interest to many of us is the problem of low complexity intrinsically disordered regions. And here is one archetypal sequence that I show you drawn from HNRNP-A1. These molecules that are of interest to many of us have this typical architecture of, multivalence of RNA recognition modules, RRMs. Also in some places, depending on what your bias is, they're also known as RNA binding domains. And often they have these low complexity domains either appended or interspersed between. Now, one thing we know for systems like this is that you can lop off the LCD and it can actually drive phase separation on its own. So it either is the main driver of phase separation or it's modulating the overall driving force for phase separation. But the key question then becomes, if you look at a sequence like this that is sort of has basically a parsimonious alphabet, what are the stickers? I mean, I have actually colored them to leave you with some breadcrumbs as clues. And notice my cursor is hovering around what I think are the stickers. But, that's come from sort of, so what we want is not to just use, human intuition, but sort of arrive at some rigorous ways of identifying stickers. So what we'll do is basically ask the following question, which is, what are the stickers in archetypal low complexity domains? And I think based on sort of the extant theories, what we can propose is that mutations to stickers will directly alter the driving forces for phase separation in sort of measurably significant ways, whereas mutations to spacers may not necessarily impact the driving forces such as the saturation concentrations, which we will talk about, but they will impact the cooperativity of phase transitions and also the material properties of condensates.
Go ahead, I have a quick
Yeah.
question. So in that prototypical protein where you had RNA binding domains and low complexity domains, and then you're going to bring in later on RNA as a component in condensates, do all the RNA protein interactions happen between just the RNA binding domain and the RNA, or are some of the stickers and spacers in the low complexity domain also interacting with the RNA?
I think that is really the burning question in the field, right? Because if you were to use simple measures like, and these are not very easy to perform with RNA, but affinity measurements in very dilute solutions, you will conclude that, these are fairly weak interactors with typical RNA molecules. It turns out that, of course, you can also demonstrate that these low complexity domains, and Geraldine Seydoux has some very nice data, and there Rohit Parker has data. And what you can demonstrate that these low complexity domains definitely house the ability to interact with RNA. In fact, what I'm going to focus on is actually, when I get to the RNA portion, purely a low complexity domain, right? And so, and we'll try to get that grammar as sort of the first step. So, the story of trying to identify stickers in a sort of systematic way started with the collaboration with our colleagues in Dresden, Tony Hyman and Simon Alberti, driven almost exclusively by Tia Wang, a postdoc in Tony's lab, and Jungmo Che, who was a postdoc in my lab. And the targets were, essentially what we referred to as FUS family proteins, but these are really FET family proteins. And all of these proteins have this very interesting bipartite architecture. So there's this prion-like domain over here in the N-terminus. There are the RNA binding domains that basically encompass arginine-rich IDRs, shown where my cursor is hovering, and then bona fide folded domains that are RNA recognition modules. A lot of these proteins have this architecture. And one of the things that you would do sort of as a conventional assay is basically to ask, as you crank up for some fixed solution conditions, as you crank up the protein concentration, at what is the threshold concentration above which you see the onset of droplets or condensates. And you can also do these spectrophotometrically. So it turns out that you can measure these saturation concentrations 2 or 3 different ways. Gia actually had 4 separate ways of doing this. They all generate reproducible results. And the number here is circa 5 micromolar for full-length FUS. What's interesting is that Gia went on to then measure the saturation concentrations at 150 millimolar potassium chloride for a series of different proteins that have very similar architectures. And the blue bars basically make the point that these sequences clearly have sequence-specific driving forces for phase separation, as evidenced by the fact that the saturation concentrations vary by up to 2 orders of magnitude. Just as a reference, here are the typical sort of average concentrations of these proteins inside cells. I put this up mainly to make the point that the cell is also sort of perhaps cares a bit about the expression levels of these proteins. But having said that, these are sort of crude numbers that are kind of context independent. But the key question is the following, which is, what are the determinants of these sequence-specific saturation concentration values? So when we were thinking about sort of what might be the underlying molecular grammar, Alex Holhaus, then a postdoc in the lab, and Jung Mo sort of thought to interrogate the proteome of intrinsically disordered regions in particular, and the entire human proteome actually, and noticed a very distinctive signature that popped up, which is that these proteins that we had sort of focused our attention on, sort of listed here, were quite, they stood out for having a combination of a high tyrosine and high arginine content compared to this red blob in the bottom left corner here, which is your garden variety protein really tends not to have a very high arginine or very high tyrosine content in terms of IDRs. So the thinking was that even though these sequences are highly dissimilar to one another from an alignment perspective, perhaps this high frequency of tyrosine and arginine, which is uncommon, might have something to do with the driving forces. So that led to a series of experiments wherein Gia went on to basically delete the prion-like domain under conditions where one can observe condensate formation for the full length. One basically does not observe condensate formation for the prion-like domain or the RNA binding domain on its own, but if you put them together in trans in solution, you actually can sort of get back a saturation concentration that's definitely closer to a order of magnitude higher than when they're in sort of tethered to one another, and that's essentially an effective concentration argument that you can make up.
So if in the trans experiment, you alter the concentrations of those 2 components, did you look at, you know what I mean? Like,
yeah, so those will definitely lead to sort of this closed loop type of phase diagram, which would look exactly like what you would observe in Mike Rosen's poly-PRM, poly-SH3. Okay. And the concentration regimes where you will define the phase boundary will be determined entirely by the valence of the arginines. And in fact, we have that prediction of what that phase diagram would look like in Furkan Dar's recent paper in PLOS Comp Biology. So it would appear that these are stickers, so you can sort of fine grain this a little more and think about the amino acid chemistry. So, I mean, you look at this and you say, well, we all know about cation pi interactions, so that's what must be what's important. So we can drill down a little more. So we've got a pi system here, a pi-ish system, so this is sort of a Y-aromatic system, if you want to call it that, essentially a planar arrangement of charge. Zhang Mo basically then said, well, okay, we can adapt the sort of published stickers and spacers model from Semenov and Rubinstein, and then come up with a framework that basically generates a prediction for how the saturation concentration should depend on the valence of this numbers of stickers and spacers. And, you know, some sophisticated mathematics later, actually what you end up is a very compact formula that says that the saturation concentration should be essentially inversely correlated to the product of the numbers of tyrosines and the numbers of arginines. And the correlation, I mean, this is a fairly crude theory because it sort of ignores some very specific spacer effects and things like that. And the correlation is actually pretty good. So it suggests that, okay, so the primary stickers in these sequences are probably, in fact, the tyrosines and arginines together. Now we started to think a bit more about these stickers. What would make a good sticker, right? So clearly arginines have charge. They have a delocalized charge distribution, so that would lead to a sort of a dipole moment just by sort of, you know, the way the electron cloud would be distributed. But they also have a planar arrangement as to the pi systems, and that could give you sort of these big quadrupole moments. The reason that becomes important is that a sticker then can encode essentially a hierarchy of interactions, right? So charge interactions will be long range, go as 1 over r. Charge dipole will go as 1 over r square. Charge quadrupole as 1 over r cubed, and so on. So what we were building up to was actually a prediction that's based on these intrinsic multipole moments that you can measure in the gas phase for these systems. So tyrosine has a finite dipole moment. Just to calibrate you, the dipole moment of water is about 2.6 dBi. So, you know, it's essentially very much water-like in that regard. It's got a substantial quadrupole moment. Phenylalanine, because it doesn't have the OH group, basically has a 0 dipole moment and roughly the same quadrupole moment as tyrosine. Arginine has a charge just as lysine would, but the charge distribution is essentially isotropic for the amine, suggesting that and in contrast to the charge distribution for the guanido group, which has this sort of planar arrangement and delocalization, giving it a substantial quadrupole moment. But so the key hypothesis that emerged was that if you were to substitute tyrosines with phenylalanines or arginines with lysines, you make for inferior stickers, right? And so let's test that. So in fact, here is, let's say, the intrinsic saturation concentration for full-length FUS in 75 millimolar potassium chloride. You make the substitute all of the tyrosines to phenylalanines. You clearly increase the saturation concentration, and in fact, it seems to be concordant with the sort of decreased sticker strength. You make substitutions of the arginines to lysines. Again, you get sort of a weakening of the driving forces as seen by the increased saturation concentration. And you get a mildly non-additive effect when you substitute all of the tyrosines to phenylalanines and all of the arginines to lysines. This becomes fully additive when you account for the fact that there are some electrostatic differences. So at 150 millimolar, they're just perfectly additive. So essentially what this says is that in intrinsically disordered regions, which we tend to think of as not encoding any obvious specificity, right? Because it doesn't have well-defined structure, so therefore you shouldn't get, you know, well-defined specificity. There indeed are these stickers and spacers, and the stickers are delineatable because they encode this hierarchy of interaction ranges and interaction strengths. And this, by the way, these are findings that are entirely resonant with, you know, results that Julie Foreman-Kay has identified and even converted into sort of a bioinformatics predictor, although they don't use the particular language of stickers and spacers. So now, you know, to sort of really get at this interplay between stickers and spacers, as opposed to just sort of predicting the effects of stickers, you really need to get at sort of this using simulations. We've developed 2 simulation engines. I will talk about one of them. So LUSSY is actually, this is published now, is essentially a way of sort of instantiating protein architectures onto a lattice. And then you can sort of, you know, do simulations of full-blown phase behavior. What I'll do is talk about an unpublished piece of work, which is based on essentially an engine that Alex Holhouse developed, whereby each IDR can essentially be written out as a single beat per lattice, and you can either learn the interactions between IDR residues, or you can sort of come up with phenomenological models. And I'll sort of demonstrate this using a particular set of examples. So first is that, there are some standard things we want to be able to do, which is, it's all well and good to be able to predict saturation concentrations once you know the identity of the stickers. What we want to be able to do is actually predict stickers de novo, and also calculate phase diagrams. And so I'll walk you through what a calculation of a phase diagram looks like. Here, what I mean by this is coexistence curves. And typically what will happen is you start up a series of simulations at some particular protein concentration, defined in terms of volume fraction. If this concentration, it happens to live inside of the two-phase regime, what you should get in your appropriately converged simulation is the formation of two coexisting phases. The tie line in this case will be horizontal because the temperature in the dilute and the dense phase should be exactly the same. But if the ordinate were salt concentration and you, let's say, got preferential accumulation or exclusion of certain ions, or let's say small molecules, then what you will actually get are tie lines that have slopes to them, right? Which is actually going to be really important for thinking about how small molecules interact with condensates, for example. There is this well-known symmetry, for example, in homopolymers, whereby in dilute phases, the chain will compact it on itself, basically indicative of the fact that it doesn't like the interactions with the surrounding solvent. But when you crank up the concentration, it swaps out those intramolecular interactions for intermolecular interactions, such that the concentration of the dense phase would essentially be the same as the concentration of these beads inside of the globule. We can actually calculate that analytically for a homopolymer. And you can show that PIMS can reproduce that, is basically what that is saying, that as you can see, the radius of gyration will increase as we increase temperature, and then concordant with that, in the regime where it is not expanded, you start to see this two-phase behavior depending on the protein concentration. So, but of course, none of these low complexity domains are homopolymers. They actually have stickers and spacers interspersed. So here is kind of a generic question that we set out to answer in collaboration with my colleague and good friend Tanya Mittag from St. Jude. This is, and the two postdocs who sort of co-drove this with Alex, or Eric Martin, and Ivan Perrin, who worked very hard on sort of some really elegant set of experiments. And so we went to HNR, the low complexity domain of HNRNP-A1. I showed the sequence earlier, but we'll zero in on the LCD, which, as a way of reminding you, is sort of the same as the prion-like domain from a compositional bias standpoint. So let's start by interrogating just the single chain behavior. So now I'll orient you in terms of what to expect. So what we've established effectively as a byproduct of this work is a well-defined protocol that you can use to identify stickers in IDRs. The reason this becomes really relevant is that those stickers are also possible targets that you can sort of manipulate using small molecules, et cetera, et cetera. So if I do a simulation of a homopolymer, the stickers will be drawn toward one another. So I should pretty much be able to see that in a movie. In fact, I won't. Unfortunately, the title of the slide gives it away, but I could have easily sort of not have put the title up, and you would have seen that, essentially what's happening is that the chain is making some transient sort of secondary structure, largely sampling an assortment of conformations, but any compaction of the chain is largely driven by these aromatic stickers or aromatic residues that are interspersed along the chain. This, by the way, is to be published in the next couple of weeks. The other thing you can do is analyze things like the radius of gyration in terms of conventional polymer scaling theories, where n will be the number of residues. There will be a scaling exponent, which, by the way, you can extract from sort of looking at radius of gyration distributions, for example. And here is simply a calibration. So if I were to make all of the interactions be repulsive, so meaning the only thing that I have here are steric exclusion, then what I get is the green distribution. If I say that there are repulsions and attractions that perfectly counterbalance one another, I get the so-called Gaussian chain, which is the black distribution. So what we have for the full-blown interaction model is the pink curve, which basically says that, yeah, the chain is trying to be well solvated, but what's happening is that these sticker interactions are trying to compact the chain on itself. You can go and do small angle X-ray scattering measurements, and by you go and do, Eric Martin goes up to Argonne at the Advanced Photon Source. He's become quite the master at doing this. What is a particularly useful technological innovation that allows us to do these experiments on intrinsically disordered domains is the coupling of size exclusion chromatography to the Sachs beamline, because historically this was a real challenge with Sachs measurements, because you would always be confounded by the aggregation prone nature of these molecules. Sachs is a sample greedy technique, needs high concentrations, and at high concentrations you're always fighting the problems with aggregation. But if you have a size exclusion column, you can effectively elute out predominantly monomeric species, and in fact you can even detect the presence of any kind of oligomerization anomalies in your sample. So here is a typical scattering form factor shown here in black dots. Eric is masterfully careful about signal to noise issues, and so effectively he's got several independent measurements. Sometimes he gets even more sort of persnickety and does measurements on two separate beamlines, just to be absolutely careful. And then from the simulated ensembles you can actually calculate a form factor, no fitting parameters involved, and you pretty much overlay on top the Sachs measurements. You get pretty much sort of concordant values for the radii of gyration. What you can do is analyze these Sachs data using what is called a molecular form factor that Josh Reback developed when he was in Tobin Sosnick's lab a couple of years ago, which gets at this sort of apparent scaling exponent. And when you fit the data, you can extract this scaling exponent. Essentially, you get something that looks like this. So just as a calibration, if the chain were to make a perfect globule, this value would be 1/3. If it were a classic self-avoiding walk, it would be 3/5. For a Gaussian chain where you exactly counterbalance the repulsions and attractions, this number would be 0.5. So it's clearly in this sort of crossover between the globule and the Gaussian chain. The other thing you can do is go back and ask, well, hey, maybe, these stickers are encoding some secondary structure, for example. So classic NMR spectroscopy will allow you to do that. Here is sort of a proton, a nitrogen HSQC spectrum. And this stands out mainly because you get this very poor dispersion along the proton axis and very sharp peaks, completely concordant with the idea that these are intrinsically disordered regions. You can deploy Julie Foreman-Kay's SSP score profile that analyzes these types of data and turn them into secondary structure propensities. And what you find is a very, very weak bias all the way through. This is pretty much in the noise. You can go back and analyze the simulation results and you get roughly similar types of patterns. Quantitatively, they're not exactly the same. But again, to go from here to a calculation, you have to actually convert to secondary structure sort of predictors based on assignments. And so then there's always some mismatch there. So then having established that the simulations and the experiments are roughly on the same page, you can actually analyze sort of a normalized sort of pattern of inter-residue distances. So when you see blue, the idea is that you effectively have sort of an expansion when compared to a self-avoiding walk. But if you start to see lots of red blobs, essentially what you're saying is that the chain is sort of more compacted in, at those regions, and those invariably involve these aromatic residues. So that led to the idea that, okay, the prediction based on these single chain studies would be that the aromatic residues in the pre-on-like domains would be the stickers. If so, a zeroth order prediction would be that a titration of the valence, i.e. the number of those aromatic stickers, should have a direct impact on, let's say, chain compaction. So we designed 3 variants. We call them arrow minus, and arrow plus, effectively that sort of, and there's a reason that we designed them the way we did, and that will become very clear in about 5 minutes time. So effectively we're titrating the valence here, and the prediction would have been that vis-a-vis the wild type, arrow minus should become more expanded, arrow minus should be even more expanded, arrow plus should become more compact. Okay, so beautiful systematic trend. These are from simulations. And by the way, those are corroborated by experiments as well. I'll get to that in just a second. So then this led us to, well, okay, it looks like the aromatic residues are the stickers. Let's just come up with a super coarse-grained model using PIMS, where now what we do is we add color to our homopolymer, right? So what we'll do is wherever we have an aromatic residue, we'll turn that into an orange bead that basically is a sticker. And then in between, we're just going to have blue beads, which are going to be spacers. We parameterize the interactions between the stickers and spacers, to be such that, and so this, by the way, is in units of thermal energy, 12 kT. This is about 3 kT. This is about 1 kT. And you essentially parameterize this model to make sure that you get back sort of the radius of gyration converting from lattices to off a lattice that sort of correlates well with the experimental value. And that's the only parameterization involved. Now we do simulations. So at this particular concentration in millimolar, so effectively what we see are, sort of dispersed phases. You see very few molecules running around in this gigantic simulation volume. Occasionally you just see them running around. I can sort of play this again. At that point, you essentially see the separation into 2 coexisting phases. You see the dilute phase concentration would be about, slightly less than 0.01 millimolar, and the dense phase coexisting concentration would be that. You can actually fit this whole, the points here come from the simulation. Getting at the critical point is a real bit of a challenge in these simulations because the fluctuations become enormous. And so we just fit to a Flory-Huggins style mean field model to be able to predict the critical temperature. And that's the 2-body, that's the 3-body interaction. And that's where this sort of curve is coming from, right? Okay, let's go to measurements on the A1 LCD. So in blue dots are the measurements from Tanya's lab that Ivan and Eric and Anna Brema actually performed. These are really painful experiments, right? And so, in blue dots are the stickers and spacer simulations. In black triangles are the actual measurements. So this particular measurement uses this nano drop methodology, where effectively what you do is you spin down the condensates, you spigot out, or pipette out is the technical term, the stuff that is in the pellet, and then you dissolve it in urea. So then you essentially you're dissolving the condensate, and then you use a spectrophotometric assay to actually measure these numbers. Very easy to describe. You need a truckload of material that just takes, it's good. The experiments are quite problematic. So given the intrinsic noise in these measurements, we reached out to a colleague, Andrea Serrano, who's at WashU, and he used FCS, and this actually is the first demonstration that you can, in certain types of condensates, use fluorescence correlation spectroscopy as a way to measure the coexisting dilute and dense phase concentrations. And actually, I won't go into this. These data also beautifully illustrate that the chain in the condensate, at least for these types of sequences, essentially is freely diffusing, is monomeric, and so effectively it effectively diffuses like it's in a very, very viscous medium, right? So having then fit to the Florey-Huggins, we could estimate the critical temperature, and then you can do a cloud point measurement to essentially sit at this concentration, go up in temperature, go down in temperature, and ask what is the concentration or temperature at which, the system becomes cloudy versus clear, and that becomes the estimate of the critical temperature. So this, in effect, becomes one of the first sort of almost fully measured binodals where you also get at the critical point. Now, let's go and sort of think about our simulation design. So again, this is showing you a movie at that particular concentration. You start to see sort of, the binodal has squished in and it has gotten shorter because we have cranked down the valence of the stickers. You go down to sort of this arrow minus minus or arrow 2, and effectively, at this temperature, it's basically a fully dispersed system. And so now we can turn to experiments. Here are the Sachs measurements that actually make the point that indeed these the chain becomes less compact or becomes more expanded as you crank down the valence, becomes more expanded as you crank up the valence. Here are now all of the binodals, right? So the circles are the points from the stickers and spacer simulations. The triangles are from the experiment. You can see that this particular sequence is inaccessible to experiment unless you find a way to go into the super cooled regime. And the fits are, the solid curves are not joining the dots, they're actually fits to the Florey-Huggins theory. And you can clearly see you titrate the valence, you titrate the driving force for condensate formation, right? Stickerology is probably quite real. But the thing that sort of baffled us originally was these are heteropolymers, and we spend all our time belly aching that, homopolymer theory really shouldn't describe, heteropolymeric systems, and yet they do. So the thing that sort of, on a complete lark, I sort of wondered if the uniform distribution of the aromatic groups along the linear chain was sort of responsible for this. And, when you have a collaborator like Alex, it becomes very easy to sort of muse something and then an hour later you have an answer, right? And so Alex then said, well, okay, you go get yourself a coffee, I'll think about this. And so what he said was that, he can come up with a sort of binary patterning parameter, sort of inspired by things that we've done in the past, where he basically asked the following question. If you treat each of the aromatic residues as the stickers, everything else as a spacer, you can basically compute a parameter omega that is going to be 1 if all of the aromatic groups are clustered together in the linear sequence, or approaches 0 if you essentially disperse them along the linear sequence. This becomes a meaningful number if and only if you have at least 20% or 15% of your residues in the sequence being stickers. This is turning out to be quite robust, by the way. And so this is a number. What does it actually mean? And this is where, if you have Alex's bioinformatics skills, you actually sort of are able to make sense of it. Because then what you can do is generate a gigantic library of random sequences and ask the following question. From an evolutionary perspective, this patterning makes sense if this is something that you would not stumble upon at random, right? So if any garden variety sequence that you pick from a bag that has this composition, has this pattern, then it's not terribly meaningful. In fact, what we find is that well over 99.99% of the sequences that you would generate at random would never have this type of well-mixed patterning. So it starts to lead us down the idea that hey, maybe this is an evolutionary fingerprint. So if you have a design principle, you can come up with a query to ask if that design principle has legs. So does the patterning of aromatic stickers matter? And so we came up with 2 types of variants. So we're keeping the amino acid composition exactly the same, which means the valence, the intrinsic valence of stickers is exactly the same. We have one shuffled variant where we lowered the omega, and another we essentially collect them up. And in fact, we actually designed even more aggressive variants. Those are just impossible to even get expressed in cells, right? And so experimental constraints sort of, we actually from a computational perspective have like 100 different variants of this. And so here, just to orient you, here's arrow perfect, here's wild type, here's arrow patchy. And this is simply showing you sort of the patterning here. So when you do simulations, you get beautiful droplets with arrow perfect, same with the wild type. With the patchy variants, effectively you start to make these very micellar looking structures that essentially are a computer manifestation of something that's just going to fall out of solution and make precipitates, right? Because essentially when you make these micellar looking systems, that's a manifestation of what you would refer to as microphase separation. And if you just, essentially what you end up with are making solid-like species. And the saturation concentrations for the, they're not microphones, sorry. At 4 in the morning when you do this, I was writing microphase separation, not microphones, we'll fix that. And so when you do experiments, you see exactly this, right? I mean, the threshold, the solubility limit just goes through the floor. These molecules just fall out of solution and become amorphous precipitates. And you know, we can reproduce this with a varying number of sequences. So essentially, the next question you go back and ask is, well, okay, you can design these things, but there are lots of sequences that have these prion-like domains, and surely enough, in all of them, the patterning of aromatic residues is uniformly distributed, right? So we were able to find a lot of well-known guys, and then we'd found this one sort of as a prediction, and then like, you know, a week later, we saw this work from Jennifer Lippincott-Schwartz talking about these ANXA7 proteins that essentially are forming condensates that basically help walk lysosomes along axons, right? And so these are, by the way, involved in vesicular trafficking at synapses. And turns out that mutations in this that screw up the patterning basically create all kinds of aberrant short-term memory problems, right? So they absolutely screw up. There are other here predictions, which means that in all of these cases, if you screw up the patterning, you're going to start seeing interesting effects. And a really beautiful outlier is actually work that comes from Elva Boca, from who, when she was working with Tim Mitchison and Tony Hyman, she'd been studying ex vivo, this protein that makes, that's essentially a scaffold for Balbi antibodies. And it turns out that the prion-like domain of ex vivo has a very strongly clustered patterning of the aromatic residues, and nothing that they could do could turn this into a liquid. It always makes these amorphous solid-like bodies, right? And so in fact, Alex and Elva are actually working to sort of test this hypothesis right now. So there are two messages in this part of the talk, which basically says, turns out that in IDRs, just individual amino acids can serve as stickers. Their valence is clearly of central importance then. And the patterning of these stickers will essentially alter the intrinsic sticker strength so as to sort of essentially control this interplay between phase separation and precipitation. And the obvious place to start thinking about this is you say, well, okay, in the context of certain types of disease-associated mutations, are you effectively cranking up the patterning, the effective valence through this linear patterning, right? I mean, you may not necessarily have mutations that are just increasing the aromatic content, but you could sort of have emergent stickers in the context of the condensate that, along the lines of what Avinash has shown over the about 4 years ago, could actually lead to sort of sprouting out these solid-like species. In the last bit, what I will do is sort of make this point that, you know, if you increase the valence of the stickers, you're basically pushing yourself toward sort of, you know, sticker-driven precipitation or aggregation. If you crank up the valence of spacers, then effectively you're cranking up, you know, essentially just network formation without condensates. And so I think the space of condensates is actually in a sweet spot, right? That sort of optimizes three things: the valence of stickers, the patterning of stickers, and the properties of spacers, right? And so I think to say that I just pick a random IDR out of the hat and assume that it's going to make condensates is a bit of a misimpression that I think has unfortunately taken hold in the literature. And so we're now in a place where I think we can start to sort of provide some guidance to how to think about these, at least these IDRs. So the obvious question is, of course, you know, there are a truckload of all of these proteins, all of these low complexity domains invariably are excised from RNA binding proteins. And we zero in on the RNA recognition modules as the players for RNA binding. But the obvious question is, what do the low complexity domains do? And so that led us to a collaboration actually with Stephen Boynem's. And I have to actually point out that I think throughout the collaboration, I don't think we had one word with Aaron. It was entirely Stephen, Alex, and myself sort of going back and forth with one another. And Venera actually did some beautiful work, which I'll talk about briefly as well. And the system we decided to sort of interrogate were an archetypal low complexity domain, sort of the C9 or 9-7 sort of, you know, dipeptide repeat system makes this really important and relevant. And we thought, let's take simple homopolymeric RNA. And I should point out here that, you know, whenever we proteinologists basically say RNA molecule, we add RNA. I was at a Biophysical Society meeting last year and somebody walked up to me and said, I don't say when I'm studying RNA molecules, I add protein, I tell you which protein I'm adding. So RNA molecules also have just the same degree of sophistication. So what the hell do you mean, you know, you add RNA, right? And so I'm learning. So of course, now we're talking about sort of a mutuality, right? So effectively in the ancient literature, now dating back 115 years, there's this phase separation used to be known as complex coacervation because you could bring together two oppositely charged molecules, and if they could find a way to neutralize their charge, realize multivalent interactions, what you would get is essentially above some threshold concentration, a co-phase separation due to the complexing of the complementary ions, not in sort of binary interactions, but in sort of, you know, a network of interactions giving rise to phase separation by complex coacervation. And indeed, in fact, you can tell I'm learning RNAology. So Tim Lohman has taught me that the way you distinguish RNA from DNA is to make sure you have the little r, so ribose versus deoxyribose. So, you know, I'm learning. Tim has also taught me that you always list all of the solution conditions because you have incredible dependence, as Tom Record has taught us over the years, on solution conditions. So under these conditions, you basically get these PR30 species making spherical condensates with adenine. You get these very irregular architectures with the guanine, the polyguanine sequences, right? So this is a beautiful methodology, which is soft X-ray tomography. It's taking advantage of the fact that essentially the absorption of X-rays, actually, or the transmission rather of X-rays, is different. Soft X-rays is different for water when compared to carbon and oxygen, and that differential transmission can be used to actually construct a full-blown image, reconstruct a full-blown image, and this is done pretty much on a regular basis at Lawrence Livermore. And so Venera was a staff scientist there, and you can actually see these spherical condensates being formed. I'll just sort of play this again, and you see these very irregular morphologies with the guanine trends. What is so special about guanine? So it turns out that one of the things that you can get with these poly-G sequences are these G quadruplexes, right? And so it would appear that the ability of the RNA to molecules to make specific types of stable structures can lead to different types of morphologies. But it leads to also a very important question, which is the impact of RNA structure on condensate morphology. Effectively, if you added this PR30 to a mixture of non-base pairing RNAs, you always get these spherical condensates. And so essentially here what we're doing is titrating the ratio of uracil to cytosine, and effectively what you see is pretty much across the entire range of ratios, what you get back are spherical condensates. Same thing with adenine and cytosine, essentially non-base pairing, and you get back spherical condensates. So that's all good. But once you start looking at base pairing condensates, this directly points to the possibility that structure is somehow impacting the nature of the condensates that you form. In the limits, you get back basically spherical condensates, but then when you start looking at sort of ratiometric mixtures, you start to see these irregular morphologies forming. And the obvious question now arises is structure somehow fundamentally altering phase separation and giving you irregular morphology so you get structured condensates? And so this dates back to sort of ideas in the 90s that came out of, Francesco Ciortino and Gene Stanley, making the point that if you had molecules that have strong cross-linking abilities, strong base pairing abilities, you can kinetically arrest phase separation, right? Because they're so busy making these structural interactions or networking interactions that you can sort of essentially get gel-like states as kinetic traps. And so one way to ask the question was to ask whether the lack of spherical morphology was essentially kinetic traps. And this is not to say that these won't be long-lived. These could be eternal, right? But you can, if they're kinetic traps, what you can do is give them thermal kicks and try to see if your system will anneal back into spherical condensates. And with a simulation engine in hand, this is what Alex actually did. So here are basically, PR30 poly-RA condensates. They fuse fairly slowly, it turns out. And this, by the way, is recapitulated experimentally as well. But when you start essentially adding base pairing abilities, you actually get these kinetically arrested things. So essentially, they're frozen in, right? I mean, but then if you essentially sort of do a thermal kick, you basically get back to the spherical condensates. And that, by the way, is exactly what you get even experimentally. So if you do subject these arrested condensates to some level of heating, and it's really close to boiling in this case, and then you anneal them back, you get back, essentially spherical looking condensates. So this filamentous network may well serve as RNA mediated kinetic traps, which is something to be thinking about. So as we think about the impact of RNA structure versus long non-coding RNAs, we get to start realizing that there are three effects of different types of RNA. There's the structured RNA that could be sort of valence limiting or valence altering. So effectively what needs to happen is the synergistic change in the RNA conformation that changes the valence, that allows the annealing back to spherical condensates. Simon and Titus, Simon Alberti and Titus Franzmann have actually made this observation with Jordina as well, that RNA entanglement actually can be a very important player in terms of sort of arresting condensate annealing.
I've got a simple question that I just missed. Is that poly-RA and RU mixed together, or is that compositionally 60 and 40%?
Compositionally 60 and 40%, yes.
Thanks.
Yeah. So the other thing that of course comes up is, now we have stickers and spacers, so we can start to think about, the sort of the nucleobase versus the amino acid, which is of course the cation. And just as a way to orient ourselves, we're now going to have the purines and the pyrimidines. And of course, we're not thinking of thymine, we're thinking of uracil in the context of the pyrimidines. So you can make condensates with purines, and you start to have these fusion dynamics really being sluggish when compared to the pyrimidines, right? And in fact, I'll quantify this in terms of these inverse capillary velocities. So you actually see lower inverse capillary velocities, indicative of sort of considerably more fluid droplets that also fuse quite readily when you have pyrimidines as opposed to purines. So effectively the polypurines, are slowing both fusion and dynamics. Now you can go back and ask, well, of course we get to choose the cation, so arginines versus lysines. And this builds on, or actually adds to rather, a recent story that we have contributed to, not just from the molecular grammar work, but also in terms of the preference of the nucleolus versus speckles for arginine-rich versus lysine-rich proteins, right? There's incredible specificity there. So here, for example, is with polypurines, you can clearly see sort of at least two orders of magnitude difference in the inverse capillary velocities. These are essentially quantifying the dynamics of droplet fusion. So you change all the arginines to lysines. Cation is cation, but the nature of the cation really matters. You basically altered the fusion dynamics. That persists even when you go to changing the purines to pyrimidines. And of course, it also depends on what type of nucleobase we have. I mean, you can see that there are the actual differences change. So quantitatively, there are differences. Here are internal dynamics, basically measuring the recovery dynamics of PR30 in the context of these different types of condensates. You can't actually see the yellow is essentially under, you can kind of see that sort of poking out, it's effectively underneath the red. So the purines are fundamentally different, so the purines down here are fundamentally different from the pyrimidines. That difference in the internal dynamics effectively is almost abrogated when you change the arginines to the lysines, right? So clearly what this is starting to say is that there is also an intrinsic valence difference in the way these cations are pointing at. So the way I like to think about arginine is really having this forked tongue, right? I mean, this Y aromaticity is enabling these sort of bidentate or multidentate interactions. But one of the things that we were really interested in, of course, is that every RNP granule is, of course, a multi-component system. In fact, you have multiple types of RNA molecules. And so if you take multiple components, what of course you can have is if I have N polymers plus a solvent and I fix the temperature and pressure, I can get N+1 coexisting phases. What do those coexisting phases look like? Here would be, let's say I have two polymers, P1 and P2, and a solvent. A homogeneous mixture would just be sort of monochromatic. A condensate that is enriched in one protein that coexists with the dispersed phase that's basically enriched with the solvent and the other polymer would look something like this. You can flip it, of course. You can get a condensate that's enriched in the two polymers that's coexisting with the dilute phase that's basically enriched in solvent or deficient in these polymers. You can get, like Amy Gladfelter has shown with the V3 system, you can have, for example, let's say two RNAs, they will actually sit in two different condensates for reasons that are slowly starting to become clear. Structure is but one component of this. The valence is of purines, pyrimidines, those actually matter a lot. Or you can get this wetting behavior, right? The nucleolus is an example of this. Nuclear speckles are an example of this. I rather suspect that every RNP granule is an example of this type of spatial organization behavior, right? Where you get this inhomogeneous distribution. And so this, and of course you can flip this around as well. So we decided to basically ask the following question. So you take mixtures of the poly-RAs, poly-RUs with our PR30 system, and then you basically titrate the ratios. These are compositionally different, so they're not in the same polymer. So these are truly 3+1 component system, namely the +1 here is the solvent. And here you actually start to see that, you know, here basically you have essentially a binary mixture. We go now to sort of different types of ternary mixtures, and then you come out again to binary mixture. And in these ternary mixtures, you're actually starting to see effectively these multi-layer droplets. You can actually go and image this using soft X-ray tomography. I love this technique. I mean, you can label free, right? You can get this beautiful sort of density organization. And the obvious question is, you know, I haven't told you which layer is which. But we asked a simple question of can we reproduce the experiments using our PIMS-based simulations. And so in effect, we have here The PRs are sort of said to be repulsive for one another. They're attractive for the adenine sequence, less attractive for the cytosine-rich one. This is based on our purine versus pyrimidine observations. So make a prediction. The prediction should be that we get poly A cores, poly C shells, and our protein is effectively diffusing freely between the two. I didn't show you the data, but in the paper, we actually make this point that is directly relevant to some recent observations about making measurements of the intrinsic mobilities of proteins and then arguing that these might not be condensates because, you know, the diffusivities might be very similar inside versus outside. What I failed to mention and show data for, but it's in the paper, is that our protein molecules actually are freely diffusing inside of these condensates. And so if you were to do FRAP measurements only by looking at the labeled protein and photo-bleaching the labeled protein and studying recovery, you would convince yourself, oh, this is a liquid-like condensate. The RNA is pretty much immobile, right? And there you would say, oh, well, this is an amorphous or solid-like condensate. So this is where I think both the client-scaffold relationship sort of seems to have a lot of legs. And so therefore, in a multi-component system, you could have molecules that are equally mobile across a phase boundary, and which is exactly what all those transcriptional hubs are, right? They're all massively multi-component systems, but you're basically measuring the diffusivities of one species out of what, n-1, right? So that's an important point to keep in mind. So here we reproduce the core cell architecture beautifully. Essentially the core is basically poly A core that is effectively wetted by a poly C shell, and the protein is pretty much uniformly distributed across, slightly non-uniformly because of course the affinity is tilting it toward the poly A core. But if we made the interactions equivalent, so in other words, we said that RNA doesn't bring any stickers to this, to the dance, so to speak. Purines and pyrimidines are created equal, so then we equalize the interactions. Now we basically don't get any spatial organization, right? So overall summary then is that there are decipherable rules for actually low complexity domain and RNA condensates. This is again tied to the multivalence of stickers, and an emerging work, what we've demonstrated is that, you know, you don't need a whopping big advantage in interaction affinities. What you really need is this combination of multivalence, patterning, and just sufficient differences in the sticker-sticker interactions versus sticker spacer to start seeing these condensates versus, right? And so RNA structure will matter, probably in terms of determining the overall timescales, because even if the thermodynamic ground state is the formation of a nice spherical condensate, all the RNA entanglement and structure formation abilities can essentially arrest these molecules in you know, sort of amorphous or filamentous structures. The arginine versus lysine composition really matters. It's turning out that in a lot of RRMs and, you know, folded RRMs, we are starting to realize that there is this, what I call Janus-like architecture, because there's a sort of partitioning of the arginines and aromatics to different faces of these folded domains. And there's an incredible specificity of, you know, the valence, the surface valence of arginines versus lysines. And so clearly these will also contribute not just to the driving forces, to the morphologies, the dynamics, overall rheology and internal dynamics, but also to the spatial organization. And so I rather feel like, you know, I think if we can sort of take a battalion of sort of low complexity domains and sort of model RNAs, and I recognize that there are differences among RNA molecules, and we should be able to sort of work out the underlying rules. And then you really, zeroth order, you would go back and ask for a particular condensate. You know, effectively, I have some combination of stickers that I'm borrowing from certain types of low complexity sequences, certain combination of spacers, and similarly from the RNA side. I think where RNA is a bit more wimpy in comparison to proteins is that its spacer architectures are not going to be as interesting, right? Because I think you can modulate condensate properties because you have a richer alphabet with proteins than you do with RNA. That other than that, I think the protein RNA sort of synergy becomes really, really important. But the one hope is that I leave you with a message that, yes, these are unstructured RNA molecules or intrinsically disordered protein molecules, entirely targetable in terms of specific interactions. You just have to sort of find the right lens to identify them. So anyway, I end there. And I think I've acknowledged people as I've gone along. I mean, there are lots of work going on from other people in the lab and other collaborations as well. But I do want to point out that I didn't call out Furkan's work quite significantly, but he is pretty much taken on the mother of all challenges of, working out how to think about multi-component condensates and not 2 and 3 components, but, hundreds of components. And stay tuned, because I think these results are going to be really fantastic. So anyway, I think we can stop there, take questions.
Thank you, Rohit. I think we have time for maybe a few more questions. I guess I'd open it to Dresden if there are questions from the Dresden site. You guys are on mute.
I was wondering if you considered to add factors that would increase the dynamics in these systems, like helicases, that would increase the structures of these RNAs, and could you insert this into your dynamics simulations?
Oh, absolutely, yeah. So you can start to think about sort of fluidizers, emulsifiers. I mean, there are a lot of these cofactors, right? And so I think, or things that sort of bring either, and the way I think about it is that you will have these cofactors. This grammar kind of helps us in thinking about this the following way. The cofactors, 0th order, you can think about as modulators of sticker valence, or modulators of sticker strengths, or modulators of the spacer excluded volumes, and so on. And so having a way to think about how might my condensate scaffold components be modified, and what are each of the modifiers doing, sort of gives us a framework for thinking about this. And so absolutely, yes, because the thing that you allude to, of course, is that a lot of these RNA binding domains also have RNA helicases, right? And in chromatin organizing systems, you have DNA helicases and various other things. And so they're active there, and you can also start to think about sort of these energy dependent or energy independent molecules that are sort of enabling unfolding and things like that. And so the other direction in which we're going is you can start to append chaperones, for example, right, that sort of then facilitate the unfolding of proteins that, or RNA chaperones and so on. So absolutely, yes. I think the framework is really robust in the regard of being able to sort of interrogate what cofactors will actually do.
Any other questions in Dresden? A more general, simple question, which is, can you, by thinking about it this way, can you say that the RNA is usually playing a scaffolding role in the condensates, or is it too early to say? Or I know it's not quite black and white.
Yeah. So I think actually, your last comment pretty much answers the question, because so I think what we are coming to is a place where we're thinking about, or not thinking, we've actually made measurements, right? Where we've got RNA concentration, and in fact here there's enough specificity in the RNA that we're choosing different RNA molecules, fix the protein, RNA concentration on one axis, protein concentration on the other. What you get is a closed loop shape to the phase diagram. That closed loop gets kind of lopped off in different regimes depending on the interplay between the RNA, protein, RNA, and so heterotypic versus homotypic interactions. The domination of the RNA interactions often occurs at very low protein concentrations and high-ish RNA concentrations. And here I'm not speaking about generic homopolymeric RNAs. I'm actually talking about very specific types of fungal RNAs that we're working on with Amy Gladfelter. So conversely, and then of course you can have, you know, protein-protein regimes as well. So the ellipse then, what Furkan has actually realized is that yes, you get a closed loop, but the ellipse kind of has dimples, gets shaved off in different regimes, the tie lines change slope, etc. Depending on, for a given stoichiometry, to what extent is the heterotypic interactions dominating over the homotypic interactions, right? And so what is nice about this is that we're establishing how to read all this just from looking at the shapes of the ellipse. And then the next thing, and you know, you cannot start making buckets and buckets of protein and RNA to sort of generate ellipsoids for every system. But there are two things that we're actually trying to solve, and I think we should be fairly close. One is that to be able to reconstruct the full closed loop based on a parsimonious set of measurements, and then use the underlying computational engines to then drive this forward. And the second thing is that, you know, if you have a bona fide granule, you probably have on the order of, you know, 700 to 1,000 separate components to think about. None of us are going to actually plan on, you know, tagging 700 molecules simultaneously. I don't think we have trouble finding 2 channels, so, you know, forget 700. So let's say we're probably going to track 2 or 3 molecules at a time. So you're working in this low dimensional space, but you actually have a multi-dimensional phase diagram that's impacting what you observe on the low dimensional space. How does the shape of the ellipse tell you what all those hidden variables are actually doing? This actually turns out to have a perfect mapping to tomography. And so in much the same way that you would use data, you know, sort of in low dimensional data to sort of reconstruct high dimensional ellipsoids or projections of high dimensional ellipsoids, you can do the exact same thing here as well. And so that's the other thing that Furkan is actually working on. So yeah.
I think we have to wrap it up. For a
absolutely
really clear presentation of some really seminal work in the field.
Thank you. Thank you. So does Dresden sign off now? Do I get to say bye-bye?
Are we no longer recording?